Given a right triangular prism ABCA 1B 1C1. Since it's a right triangular prism, the side edges must be perpendicular to the base, meaning they're perpendicular to every line in the base. In other words, AA1 is perpendicular to AB and AC. BB1 is perpendicular to BA and BC, and the same applies to CC1. It says the side face ABB1A1 is a square. Since it's a square, we have right angles, and what else? The sides must be equal. Okay, it also says AB equals BC equals 2. Since it's a square, that means AB equals BB1, which equals AA1, all being 2, and BC is also 2. Now, we don't know AC yet. Okay, E and F are the midpoints of AC and CC1, respectively. Point D is a point on the edge A1B1. Which point exactly? We don't know, right? But it's somewhere on this edge. Now, it satisfies that BF is perpendicular to A1B1. BF is right here, perpendicular to A1B1. Since A1B1 and AB are parallel, it means AB is perpendicular to BF. As mentioned, BB1 is perpendicular to AB, so AB must be perpendicular to the side face BC C1B1. Naturally, it's perpendicular to any line in this plane, including BC, so we find that this angle is a right angle. Since it's a right angle, it means at point B we have mutual perpendicularity, so we can set up a coordinate system. So that's the idea. Now we need to prove BF is perpendicular to DE. Since point D is moving, and we've already proven the mutual perpendicularity here, what can we do? We can set up a coordinate system. After setting it up, vectors BF and DE will be perpendicular. This means that when we approach this, instead of using just the previous properties, criteria, and various theorems for derivation, which can be quite tedious, we can use space vectors to handle it. Okay, let's first establish the perpendicularity mentioned earlier. In the right triangular prism, A, B, C, A1, B1, and C1, these are the points we are considering. In this case, we must have the line segment A1, B1 parallel to the line segment AB. Additionally, any side edge, such as BB1, must be perpendicular to the base, specifically perpendicular to the base ABC. Since it is perpendicular to the base plane ABC, the line BB1 is, by definition, naturally perpendicular to any and every line that lies within that plane, including, of course, the line segment AB. So the fact that AB is perpendicular to BB1 is now settled and established. Now, since the lines A1, B1, and AB are parallel to each other, and because you told me that BF is perpendicular to A1B1, and since AB is parallel to A1B1, we can conclude that BF is perpendicular to AB. Look closely, AB is perpendicular to BF, and AB is perpendicular to BB1. BF and BB1 intersect at a point called point B. Okay, and because at this position, BF and our BB1 intersect at point B, and furthermore, our BF here must be on this side face, BCC 1B1. At the same time, BB1 is also definitely on this side face, BCC 1B1. So we immediately get that our AB here must be perpendicular to this side face on the right, which is BCC 1B1. Obviously, we use the determination theorem for line plane perpendicularity here. Since it's perpendicular to this plane, by definition, it must be perpendicular to any line within it. Therefore, AB is perpendicular to a line BC within this plane. And because AB here is equal to BC, which equals 2, so it means that triangle ABC is a right triangle. There's an isosceles right triangle. A right triangle, which is a triangle with one right angle. So at this particular position, the line segment AB is perpendicular to the line segment BC and also to BB1. Is also perpendicular to BC. Meanwhile, BB1 is also perpendicular to our AB here. So next, we can set up a coordinate system. Let's use B as the origin. To set it up, BX, Y, Z. Good indeed. X as shown, Y, Z. Okay. Because at this particular position, In order to confidently say that it's a square, we really need to know its length. Since this side face, AA1B1B, is a square, and EF are the midpoints of AC and CC1. This means we can find the coordinates of these points. Point B's coordinates are, of course, at the origin 0, 0, 0. Then, at this position, let's look at point F's coordinates. Since point F is on this plane called YBZ, in the YBZ plane, its x-coordinate is 0. Its y-coordinate is exactly BC, which is 2. Its z-coordinate, since CC1 equals 2, CF is exactly 1. Next, we need to know point D's coordinates. Since point D moves along the line A1B1, we don't know its exact value yet, which means at this position. You can represent it using BED. You can also set B1D at this position to lambda. All right, let's set it up. So in this case, let's define it clearly. After setting it to lambda, its x-coordinate is lambda, and its y-coordinate is 0 because it's exactly on the xbz plane, and its z-coordinate is bb1, which is exactly 2. Next, for the coordinates of point E, since E is the midpoint of AC, if we drop perpendiculars to the x and y axes, it's right in the middle, so it's 1, 1, 0. From this, we can find vector BF. Vector BF is exactly equal to 0, 2, 1. At the same time, vector DE or ED can also be found. Vector DE is 1 minus lambda. 1 minus 0. Then 0 minus 2 is negative 2. We find the dot product of vector BF and vector DE. 0 times 1 minus lambda is 0, 1 times 2 is 2, and 1 times negative 2 is minus 2, which equals 0. So BF must be perpendicular to DE. By using vectors as a tool, we don't need to worry about where point D is, because no matter what, when you multiply by 0, it disappears. Okay, following this logic, it asks for what value of B1D, which is lambda, the plane B, B1C, 1C, and plane D, FE form a dihedral angle with the minimum sine value. For the sine to be minimum, we actually need the cosine value to be maximum, so at this point, we need to find its normal vector. From the diagram, it's easy to see that for plane B, B1C, 1C, the normal vector is, let's discuss the normal vector, which we will refer to as vector M. Since this plane is exactly the YBZ plane, we can write a simple normal vector for it as 1, 0, 0. Next, we need to determine the coordinates for points D, E, and F. We already have the coordinates for point D, so let's write them out again for clarity. Lambda 0, 2. Point E is located at 1, 1, 0, and we also have point F at 0, 2, 1. So now at this stage, you'll definitely need to generate the next steps based on these points and the information we've just reviewed. A vector related to D, which might as well be vector DE. Vector DE turns out to be 1 minus lambda. 1 minus 0 is 1, and 0 minus 2 is negative 2. Similarly, vector EF can be found. 0 minus 1 is negative 1, 2 minus 1 is 1, and 1 minus 0 is also 1. Okay, now that we have these two vectors, we can set it up. Let us denote the normal vector of the plane, which is defined by the points D, E, and F as the normal vector of this plane DEF. Vector n, which equals x, y, z. I just need to solve for x, y, and z here. Then, based on the given conditions, the dot product of vector DE and vector n equals 0. And the dot product of vector EF and vector n is also 0. At this point, you can write out a relational expression. This part is just for show, to get those points for showing your work, right? Writing it down, we get 1 minus lambda times x plus y minus 2z equals 0. Negative x plus y plus z equals 0. Now, what are we actually doing behind the scenes? I'll use the blue pen and that little trick we discussed earlier. This method lets us find the normal vector quickly. It's especially fast when dealing with parameters like this. So we take 1 minus lambda, and what do we do with these two vectors? Write them twice in the same row. So we get 1 minus lambda, 1, negative 2. Write the bottom one twice too. Negative 1, 1, 1, negative 1, 1, 1, then cross out the ends. Next in the middle, we cross multiply and subtract adjacent pairs. For the first set, 1 times 1 minus, 1 times negative 2 gives us exactly 3. For the second set, negative 2 times negative 1. When cross multiplying, you must subtract in the same direction. For example, top left times bottom right minus bottom left times top right. Stick to that order. You could also do bottom left times top right minus top left times bottom right. Either way is fine, just be consistent. Okay, -2 times -1 is 2, minus our 1 minus lambda, which results in exactly lambda plus 1. Next, 1 minus lambda times 1 is 1 minus lambda. Then subtract -1, which gives us 2 minus lambda. Thus, we found vector n here. It's 3 lambda plus 1, 2 minus lambda. So this means that during this process, you need to know how to, well, pretend to write out the steps for this part, which is, let's assume x equals 3. Then we can calculate that y is lambda plus 1 and z is 2 minus lambda. That's how we solve for lambda here. Okay, now that we've found these two normal vectors, we can calculate the cosine of the angle between them. Cosine A. The angle between vector m and vector n is equal to the dot product of m and n, which is then divided by the product of their magnitudes. This calculation shows how the two vectors are oriented with respect to each other. Now, when dividing, we already have vector m as 1, 0, 0. Multiplying that, the numerator only has a value from the x-coordinates, and the magnitude of m is simply 1. Then the magnitude of the following part is the square root of, let's see, the square of the x-coordinate. 3 times 3 is 9, plus the square of the y-coordinate, lambda plus 1 squared, plus the square of the z-coordinate, 2 minus lambda squared. From this, we can further simplify it. The numerator remains 3. As for the denominator, well, let's take a look. There's a lambda squared here and another lambda squared there. So the result is exactly 2 lambda squared. Okay, we have 2 lambda here, and then subtract 4 lambda. So we're left with minus 2 lambda. All right, we have 9 plus 1 squared plus 2 squared here. 9 plus 1 is 10 plus 4 makes 14, so it equals 3 over. After you factor out a 2, you'll find the denominator is a quadratic expression in terms of lambda. It's a quadratic under the square root, so let's complete the square. That gives us lambda minus 1/2 squared. Now we have the 2 lambda squared and 2 times lambda times -1/2, then multiplied by the 2 in front. We also have the -2 lambda. Now 1/2 squared is 1/4, times 2 is 1/2. We've added an extra 1/2, so we need to subtract 1/2 and then add the 14. The result is exactly 3 over the square root of 2 times lambda minus 1/2 squared. Then plus 27 over 2. Obviously, to minimize the sign value here, we need to maximize the cosine value. To maximize the cosine, the denominator must be minimized. So to make our value for the sine function, as calculated, minimum. Therefore, the cosine value here must be maximum. Then when lambda specifically is equal to 1/2, the cosine value at this point is at its maximum. Since the cosine is maximized, the sine of this dihedral angle is also maximized. All right, so to conclude, when B1D equals 1/2, we find that the sine of this dihedral angle is at its minimum. The question didn't ask us to find the actual minimum value. Of course, if you're interested and have time and you're feeling calm and unhurried during the exam, you could go ahead and calculate it, okay? The key point here is to be clear about the method for calculating the normal vector. Write it twice in the same row, then remove the ends and do the cross multiplication. When subtracting the cross products, make sure the order is consistent, and then you can find the value for this. A normal vector